Okay, in this video, we're going to talk about the second type of reaction. So we're going to learn in Module 6, which is acid-base reaction. Okay, now by name, we can easily tell this reaction is going to occur between an acid compound and a base compound. Okay, so let's take a look at how do we know what acid-base compounds look like, or how do we know it's acid-base in the first place? Okay, so first of all, we already know what acid look like. Acid basically look like H something, okay? And the key feature about acidic compound is in water. This is very important, okay? In water, the acid, you can see that before it goes into water, HCl is actually a gas, and once it dissolves, it turns into aqueous solutions. In aqueous solutions, okay, basically behave just like any other ionic compounds, deassociate into H plus, which you already know that it's called a proton. Okay, it is a proton without electron, and the chloride with negative charge. So it's just like ionic compound. Okay, so that's for base. Acid, I'm sorry. Base, okay, any compound can do this in water, having an OH. Okay, so I'm gonna highlight the core part of the acid base. Okay, OH, which is called hydroxide. Okay, this is called the hydroxide ion. Hydroxide ion is the key feature of base. Now, you can see this is cation and anion. Cation, anion. So we're gonna do the same like double replacement reaction. Okay, the cation, which is proton, will bond with the OH hydroxide, and the other two ions will bond together. So after this cross link, you can see that you can have any different kinds of acid base, but guaranteed the product is going to be HOH combination, which is going to be water. So one of the key features about the acid-base reaction is that it forms water. Okay, whereas the other compound, obviously, if it was going to be the other products, okay, it's going to be another ionic compound. So remember two things: acid were to deassociate into proton ions, or bases are usually produces hydroxide ions, okay, when dissolved in water. Usually people, just want to briefly introduce this, okay, usually people will talk about strong acid, strong base. What does that mean, okay? What do you mean by strong acid, strong base? Here, first of all, we're going to take a look at a few examples of strong acid, strong base, such as you can see all of the acids here with, HHH, so hydrochloric acid. You can practice this practicing the module 5 naming system, okay, without oxygen, hydrochloric acid, hydrobromic acid, hydroiodic acid. Keep in mind all of the H are +1 charge, okay, so make sure you know how many hydrogens here. HNO3, you have to know NO3 is nitrate, so this is nitric acid. Sulfate, sulfuric acid, and challenge yourself with that question, why there's a 2 down here, okay? Because sulfate is negative 2 charge, H is +1 charge for sure, so you can balance charge by putting the 2 down here. ClO4 is perchlorate, so the acid will be perchloric acid. Okay, so these are strong acids, and there are many other different kinds of strong acids. Okay, but here are a few examples of them, and here are a few examples of strong base. So you can see hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide. The same thing. Hydroxide, each one has -1 charge. So these are lithium, sodium, potassium, rubidium. They're all +1 charge because they all belong to group 1. And also, you want to challenge yourself here. Why there's 2 here? Even though these are also bases, okay? That's because calcium, strontium, and barium, they are +2, group 2 metals, so they have +2 charge, whereas hydroxide is -1 charge. So in order to balance charge, you have to have 2 hydroxide. With the parenthesis, you're going to put 2 outside. Okay, these are strong bases, okay? All right, so the most important thing, or if you want to understand what strong acid base are compared to relatively weak acid, weak base, okay, it's very simple. Let's move back to, no, I can rewrite here. For a weak, strong one, okay, let's say for a strong one. Doesn't matter if it's acid base, I'm going to use acid for example, okay. Now for strong acid, H. I'm just use A generally indicating this is an acid. Okay, it does this. Well, isn't that what all of the acid does? Not exactly. So let's say you have 100 molecules of acid. Okay, and you're gonna have 100 protons and 100 of whatever the counter ion is, and this 100 molecules of acid will be gone. Okay, everybody will deassociate into pieces. Now, whereas the weak one, let me use a HA prime recipe and the weak one. Okay, it does the same. Okay, almost. Okay, but you may have start by 100 of these, but you only end up maybe 3 of these, 3 of these. That means there will be 97 that's left over. So you see here is the ratio, is the efficiency of the acid that makes them stronger or weaker relatively. Okay, so that's basically same with base as well. Okay, all right. So what we need to learn here is if you're given 2 compounds, first of all, do you recognize them to be acid and base? And so you can predict they can undergo acid-base reaction. And in turn, are you able to write out the products and then balance the equation? Okay, so first of all, let's look at this half reaction. You can see there are 2 chemicals, both are in aqueous solutions, single arrow, missing the other half, the product half. Okay, now first of all, you have to recognize that, okay, this is an acid base, hydroxide. All right, the name of this guy is a potassium hydroxide. The other guy is sulfuric acid. Okay, sulfate. 8 turns to ec acid with oxygen. Okay, sulfuric acid is H2 here. Now, what we usually do is you should think about the cation anion. Okay, first of all, the cation of this compound it's very similar to double replacement reaction, to be honest. Okay. The cation of this is K plus and OH minus. And the anion of this is, the cation of the other compound, I'm sorry, is H plus and sulfate. Notice that I didn't bring this 2 down here, okay, because this 2 does not belong to proton. It shows you there are 2 protons. Okay. All right, so the new products between them is going to be, first of all, water. Okay, water is a guaranteed compound products for acid-base reaction, and always be aware this is liquid L. Okay, not aqueous. It is aqueous, but it's not aqueous solution. We already talked about this in the previous video. Okay, you should list the water as liquid, gas, or solid, depends on the condition, but it's not AQ. Now the other products is going to be between potassium and sulfate. When you put them together, okay, you should put the potassium in the front as it's a metal. And you have to think about this is a positive 1 charge. The charge is the key, okay, negative 2 charge. So in order to balance the charge, you need 2 potassium. So in order to show 2 potassium in the compound, okay, you can only put the 2 down here. So that's K2 sulfate, potassium sulfate. All right, so this is how you write out the products. Now, how do we balance this kind of equation? Of course, you can do the same thing as we did in the double replacement, but here I want to introduce you another way of balancing acid-base reaction, but only for acid-base reaction, okay? So this method applies to acid-base reaction only. Now, when you look at the acid-base reaction, all you need to focus on is how many hydroxide do I have and how many protons do I have producing to equal number of water molecule. So basically, if you have 1 hydroxide, you need 1 proton, and that's going to produce 1 water. Or if you have 2 hydroxides, it has to have 2 protons to react with it or to neutralize it into 2 water molecules. Okay, so you are going to have equal number of these 3 guys. We're not trying to balance oxygen, hydrogen, or any individual elements. We're trying to balance hydroxide as one whole thing, proton as one whole thing, and the water molecule as one whole thing. We need to make them equal. Now, when you look at this unbalanced equation, any unbalanced equation, assuming everybody has a number 1 in the front, okay, before you start it, that's what it is. Look at how many hydroxide it has. Okay, yes, it has 1. Look at how many protons it has. You basically H2, H3, how many ever it is, that's how many it has. How many water molecule? Of course, it's 1. Now, in order to balance these 3 guys, okay, you have to make them equal. So this is 1, 2, 1. That's not going to work. So you got to make everybody 2, since this guy is 2. And that's going to be coefficient going from the corresponding compound. In order to double hydroxide, again, when balancing equation, you never put the little numbers inside the molecule. Okay, you should always put a big number in front of the molecule. You need nothing here because you already have two protons. That's actually the reason why we want double everybody else, 2 waters. Now, by doing this, you should already balance the entire equation. By saying that, okay, you can check all of the elements, okay, before and if you're separating the equation from products, the products from the reactants, you should see the same amount of each element from left to right. You can see, for instance, you have 2 potassiums and you have 2 potassiums. You can see you have 1 sulfur, you have 1 sulfur. Now hydrogens, you have 2 hydrogens here, 2 hydrogens here, that makes total 4, and you have 2 by 2, that's 4 hydrogens as well. Okay, oxygen is going to be a little bit more complicated. Okay, overall on the reactant side, you have 2 hydroxide here. That means there are 2 oxygens, and there are 4 more oxygens from sulfate. Since there's no number here, that means there's 1. Okay, so 2 oxygens plus 4 oxygens, that's total 6 oxygen. Okay, now here you have 2 water molecules. That's 2 oxygens, 4 oxygen from sulfate as well. So that's 6 oxygen as well. Okay. So you can see even though we use a different method, okay, but still the result should be the same. All of the elements should be balanced already. All right, let's take a look at another example, okay. All right, so of course, feel free to pause the video here, try it out yourself on the paper, and then play back. All right, so first of all, you should ask yourself is, do I recognize this is an acid? Or can you name it? Do I recognize this as a base? Can I name it? All right, this is called hypochlorous acid. It's because this guy, ClO, is called a hypochlorite. Okay, so you keep the original name and then change IT to us acid. So it's called hypochlorous acid. Now the other guy is called aluminum hydroxide. Okay, aluminum is the type 1 metal, so you don't need to say aluminum 3 hydroxide or aluminum trihydroxide. Just say aluminum hydroxide. Positive 3 charge, negative 1 charge. That's why you need a 3 down here. And always remember, okay, if you want to show mutability of polyatomic ion, you need to have a parenthesis. Okay. But anyway, this is an acid-base reaction. Okay, acid and base. Water is one of the key products, and then you can almost automatically kind of, link the other compound by writing out the other compound by putting the cation and anion together. Okay, so you would have Al in the front, metal in the front, and ClO. All right, so is that it, the compound? Nope, you have to balance the charge. Aluminum is plus 3 charge. This whole thing, ClO, is called hypochlorite, is negative 1 charge. Now, if you're not sure or uncertain the charge, or if you forgot it, okay, look at this. Look at this guy. Hydrogen is plus 1, and you're given formula of this. By default, this formula should be neutral. So the rest of the ion, there's only 1 hydrogen. The rest of the ion must be negative 1. Otherwise this is the wrong compound. Similarly, you can remember, okay, or at least you should remember, hydroxide is negative 1. So when there are 3 hydroxides and only 1 aluminum to balance with it, so aluminum must be plus 3. All right, so that's kind of way you can take the information that's actually hidden from the original problem. Okay, but anyway, so if you know that aluminum is plus 3, ClO is negative 1. In order to balance this charge, you need to make this whole thing 3. Okay, so by putting the 3 down here is not good enough. You have to cover the whole thing up with the parentheses. Okay, all right, so let's look at the balance equation. Now again, focus on these guys only. Okay, now there's only 1, there are 3, because this compound naturally has 3 of it, and this is only 1 water. So you need to multiply this by 3, multiply this by 3, because of this number 3. So you need a factor of 3, another factor of 3, and that's it. Still, so even though it doesn't look like that, but you actually just balance the entire equation. So just one quick question: is that, it seems like you only need to worry about these 3 compounds? Is that always true that this guy should never be touched when balancing equation? Like there should be always 1? The answer is yes. But this again, this applies to acid-base reaction only. Okay, I can't overjudge this. Just look at the part of the molecule of each, and then you can balance them, and that works on for acid-base reaction only. Okay, so this is for acid-base reaction.